In this video, we'll talk about a problem in the Putnam mathematical competition in the year 2016. The problem asks us to evaluate a sum with two indices, k and n. So this is a double sum. Let us first make an observation. If we denote this sum by S, we observe that S is absolutely convergent. It is always very good to have the absolute convergence when we deal with infinite sums, because then we can do a lot of things with it. For example, for this double sum, if it is absolutely convergent, we can change the order of the sum, or split it, or change the order of summation. We can do a lot of good things with an absolutely convergent infinite sum. So why is it absolutely convergent? Now we take the absolute value of the summons. The trick here is to separate k from 2n so that it will be easier for us to estimate this double sum, because then we can sum it up separately. So what we do is that we're gonna pull out k times 2 to the n. Now this part is less than or equal to 1. So we can majorize this to this double sum of 1 over k squared times 1 over 2 to the n. Now it's good. And we can sum it up and make a product. Those two terms are both finite. So the whole sum is finite. So this guy is absolutely convergent. Very good. And now let me present the solution due to Liang Xiao. There are many solutions to this problem, but I really like his solution. The idea of the solution is the following. If you look at this double sum, there will be plus minus 1 in the coefficient. So the first idea is to split this sum into two parts. In one part, you get all the plus ones. In the other part, you get all the negative ones. And the proof goes as follows. We write S as S0 minus S1, where S0 represents the sum when this is plus 1. So this is sum over those cases where k is odd. And correspondingly, we consider a case where k is even. And we look at that part of the sum. Here we can do this because of the absolute convergence. And now let us play with this even part. This S1, because k is even when we take this sum, we can replace this k by 2l. Now here's a very interesting trick. Instead of summing this up from n equal to 0, we're going to sum it from n equal to -1. And of course, we have to subtract the term when n is precisely equal to -1. That term contributes to this sum. When n is -1, this is just L plus 1. The part we subtract is very good. This part can be split into telescoping sum. So let's call it part 2, and this part 1. Part 2 is easy to handle because it's just equal to -1/2 times 1/1 times 2 plus 1/2 times 3 plus, this is telescoping because I guess you are familiar with this. You can split each fraction as the difference, and you can see it is telescoping. Good. And this gives us just -1/2. And now let us look at the first part. The first part can be rewritten as, if you make a change variable, the first part is equal to this. Here we are changing n plus 1 to n. We are replacing n plus 1 here because 2 times 2 raised to the power n is 2 raised to the power n plus 1. We change n plus 1 to n and sum it up from n equal to 0 to infinity. This is what we get. And here, we make an observation that this guy is precisely equal to, we pull out this 1/2, this is equal to 1/2 times S0 plus S1. So comparative is our definition of S0 and S1 here. This is precisely equal to 1/2 times S0 plus S1. Because when you combine them, they're just the sum from k to 1 to infinity, ignoring evenness and oddness. Which is exactly what's going on here. Now, S1 is equal to the sum of part 1 and part 2. Which is 1/2 times S0 plus S1 minus 1/2. Or if you multiply both sides by 2 and move those quantities around, you get S0 minus S1 is precisely equal to 1. But S0 minus S1 is our S. So our S is equal to 1. And we are done with the evaluation of this double sum. So this solution is really smart. There are a lot of clever observations. And this really funny trick